Welcome to this model. In this model, we are going to see about TCP IP Protocol Suite. The TCP IP Protocol Suite was developed prior to the OSI model. Therefore, the layer in the TCP IP Protocol Suite do not exactly match those in the OSI model. The original TCP IP Protocol Suite was defined as having only 4 layers, that is host to network, internet, transport and application. However, when TCP IP is compared to OSI, we can say that host to network layer is equivalent to the combination of physical and data link layers. The internet layer is equivalent to the network layer, and application layer is roughly doing the job of the presentation and application layer, with the transport layer in the TCP IP taking care of part of the duties of the session layer. So, we assume that the TCP IP protocol suite is made of 5 layers: physical, data link, network, transport and application. The first 4 layers provide physical standards, network interfaces, internetworking and transport functions that correspond to the 4 layers of the OSI model. And the 3 topmost layers in the OSI model is represented in TCP IP by a single layer called application layer. That you can see in this diagram. The TCP IP is a hierarchical protocol made up of interactive models, each of which provides a specific functionality. However, the models are not necessarily interdependent. Whereas the OSI model specifies the function belongs to each of its layer, and the layers of the TCP/IP protocol suite contain relatively independent protocols that can be mixed and matched depending upon the needs of the system. The term hierarchical means each upper layer protocol is supported by one or more lower level protocols. At the transport layer, TCP/IP defines 3 protocols: transmission control protocol, user datagram protocol and stream control transmission protocol, that is SCTP. So at the network layer, the main protocol defined by TCP/IP is the internetworking protocol, that is IP. There are also some other protocols that support data movement in this layer. At the physical and data link layers, TCP/IP doesn't define any specific protocol. It supports all the standards and property protocols. A network in a TCP/IP internetwork can be a local area network or a wide area network. At the network layer, or more accurately, you can say that internetwork layer, TCP/IP supports the internetworking protocol IP. In turn, uses 4 supporting protocols, that is ARP, RARP, ICMP and IGMP. Each of these protocols are particularly defined. Now let us see one by one. And internetworking protocol is the transmission mechanism used by TCP/IP protocol. It is unreliable and connectionless protocol that is a best effort delivery service. The term best effort means the IP provides no error checking or tracking. IP assumes the unreliability of the underlying layers and does its best to get a transmission through its destination, but with no guarantees. IP transports data in packets called datagrams, each of which is transported separately. Datagrams can travel along different routes and can arrive out of sequence, or it can be duplicated. IP doesn't keep track of the routes and has no facility for reordering datagrams once they arrive at their destination. The limited functionality of IP should not be considered a weakness. However, IP provides bare-bones transmission functions that free the user to add only those facilities necessary for a given application and thereby allows a maximum efficiency. The address resolution protocol is used to associate a logical address with a physical address. On a typical physical network such as LAN, each device on a link is identified by a physical station address, usually impaired on the network interface card, and ARP is used to find the physical address of the node when its internet address is known. The reverse address resolution protocol, that is RARP, allows a host to discover an internet address when it knows only its physical address. It is used when a computer is connected to a network for the first time or when a diskless computer is booted. The Internet Control Message Protocol is a mechanism used by hosts on gateways to send notification of the datagram problems back to sender. ICMP sends query and error reporting messages. The Internet Group Message Protocol is used to facilitate the simultaneous transmission of a message to a group of recipients. Traditionally, the transport layer was represented by TCP IP by two protocols, TCP and UDP. IP is the host-to-host protocol, meaning that it can deliver a packet from one physical device to another. UDP and TCP are transport layer protocols responsible for delivery of a message from process to another process. A new transport layer protocol, SCTP, has been devised to meet the needs of some newer applications. The user datagram protocol is the simpler of the two standard TCP IP transport protocols. It is a process-to-process protocol that adds only port address, checksum, error control, and length information to the data from the upper layer. The transmission control protocol provides full transport layer services to applications. TCP is a reliable stream transport protocol. The term stream in this context means connection oriented. A connection must be established between both ends of a transmission before either can transmit data. At the sending end of each transmission, TCP divides a stream of data into smaller units called segments. Each segment includes a sequence number for reordering after receipt, together with an acknowledgement number for the segments received. Segments are carried across the internet inside the IP datagrams. At the receiving end, TCP connects each datagram as it comes in and reorders the transmission based on sequence number. The Stream Control Transmission Protocol, that is SCTP, provides support for newer applications such as voice over the internet. It is a transport layer protocol that combines the best features of UDP and TCP. And the application layer in the TCP IP is equivalent to the combined session, presentation, and application layers in the OS model. Many protocols are defined at this layer only. Right. Now, let us define one by one. We can say that the physical layer is responsible for carrying the individual bits in the frame across the link. Although the physical layer is the lower level in the TCP IP protocol suite, the communication between two devices at this physical layer is still a logical connection, because there is another hidden layer in the that is the transmission media under the physical layer. Two devices are connected by a transmission medium. We need to know that the transmission medium doesn't carry bits, it carries electrical or optical signals. So the bits received in a frame from the data link layer are transformed and sent to the transmission media, but we can think that the logical unit between the two physical layers is two devices, and two devices is a bit. So there are several protocols that transform a bit into a signal. And next, what we are going to see is about the data link layer. And we have seen that the internet is made up of the stream, the several links like LAN, WAN connected by routers. There may be several overlapping sets of links that a datagram can travel from the route to destination. The routers are responsible for choosing the best links. However, when the next link to travel is determined by the router, the data link layer is responsible for taking the datagram and moving it across the link. The link can be a wired LAN with a link layer switch, or a wireless LAN, or wired LAN, or a wireless WAN. We can also have different protocols used with any link type. In each case, the data link layer is responsible for moving the packet through the link. TCP/IP doesn't define any specific protocol for the data link layer. It supports all the standards proprietary protocols. Any protocol that can take the datagram and carry it through the links suffices for the network layer. The data link layer takes a datagram and encapsulates it in a packet called frame. So we call that encapsulated packet as frame in data link layer. And next, let us move on to network layer. The network layer is responsible for creating a connection between the source computer and the destination computer. The communication at the network is host to host. However, since there can be several routers from the source to the destination, the routers in the path are responsible for choosing the best route for each packet. We can say that the network layer is responsible for host-to-host communication and the routing the packet through possible route. Again, we may ask ourselves why we need the network layer. We could have added the routing duty to the transport layer itself and dropped this layer. But one reason, as we said earlier, is the separation of the different tasks between different layers. So the second reason is that the routers do not need the application and transport layers. Separating the tasks allows us to use the fewer protocols in the routers. Thank you.